Hello guys, welcome to session number 10 of our KCET 2023 one-shot revision series. Today's topic will be mechanical properties of fluids, and as you can see in the bracket it says 1.01, which means approximately one question has come every year. So yeah, this is quite an important chapter. And another thing is, under this there would be fluid statics, fluid dynamics and surface tension, which means there will be many topics. However, this chapter is not as huge as you might think, but yeah, there are many topics. So I'll be highlighting most of the formulae because there will be many formulae and it would take time putting a box around them. And another thing is, I'm using a mouse, so please do pardon me for the bad handwriting while I'm writing on screen. I'm not using a writing pad. So I'll be continuing the first topic. As you can see, it's written basics, which means this will be the basic requirement for the chapter. Not a requirement exactly, but basics of the chapter. So this will be formula number 1, which we know density is going to be denoted using this symbol over here, which is called as rho throughout the chapter, which is equal to mass by volume. And then let's say there is a mixture, then we can write overall density is equal to m net by v net, which means overall mass by overall volume. And another formula you have to know is RD/SG, which means relative density or specific gravity, which is defined by rho divided by rho of water at 4 degree, which means density of the body divided by density of water at 4 degrees Celsius, which is a standard value, that is 1 gram per cc. So yeah, we need to know the formula, however, so I'll be just highlighting the formula. And obviously this formula which everyone might know, which is pressure is equal to force by area, and force is going to be perpendicular to the area of contact or area of application. So P is equal to F by A. And do not get confused with rho and P. I've just mentioned it over here. So next one would be variation of pressure with height. So I've used short forms to save space, which in this case, as you can see, there is a flask which is of this specific height, as you can see, let's say H or something like capital H. So we need to know the pressure at the point A in the flask. So the pressure, as you can see, at point A is equal to P naught plus H rho g, where over here small h is going to be the height of the point where we need the pressure from the surface, and P naught is atmospheric pressure, by the way, which is going to be outside, and I've denoted P naught everywhere else. So you have to know that P naught means atmospheric pressure. So yeah, this is going to be another formula, not a formula exactly, but yeah, this is going to be conceptual formula, which means it depends on the application. Next one would be Pascal's law. So the actual law would be in your NCRT. So it's something about the pressure being distributed equally in confined line along the line. So I've just drawn the visualization of it. So let's say there is this kind of a contraption, and we have to note that the condition over here is that the liquid should be the same in this part and this part. So in that case, if no matter how the thing is shaped, the pressure at the point along the same line. So that's another thing which I've highlighted over here, along the same line. Like over here the line is over here the dotted line, as you can see, which has point A and point B, and this is at a height h from the surface of the liquid. So in that case, pressure at point A is equal to pressure at point B, which is equal to P naught plus H rho g, just like how we saw in the above case. It's going to be the same. So yeah, that is going to be Pascal's law for you. And then we have hydraulic machine, and in hydraulic machine, as you can see, there is going to be this kind of a setup where this slab, as you can see, is the point of application of force F1, and it has, let's say, area A1. And over here, let's say the point of output of this force F2 is having an area A2, and the car is over here. So how these machines work is that we have to know the main concept behind this, which is pressure one is equal to pressure 2. So using the formula F by A, we'll be able to equate it, and we'll be getting this formula, which, as you can see, implies that if A2 is greater than A1, like if this area is it's more greater than A1, if that's the case, then even force 2, which means the output force, will be greater than F1. So by just using small force, we are able to get a larger force by just increasing this area. So this is something which you might have learned in class 10. It's hydraulic machine, how they work and how it makes our life easier. So then this would be called as type, and as you know, I'll be completing types of problem and stuff. So do not skip it in this chapter, because there will be around 7 types of problems, which means 7 types of concepts also. So the first type, even though the numbering is a bit different, do not mind it, but yeah, I've made sure that I've completed the 7. It's in a different order. So the first one, as you can see, there is a flask, and it has some liquid, and it has a mass m placed, a weight, something like mass m is placed on this slab, just like how the slab is over here, it's over here also, and then there is m. So when you place this m on this slab, the pressure at point A is going to be P naught plus H rho g, just like how we saw in the above case. But over here there's an additional pressure, and as you know, pressure is given by force by area. So over here force is going to be mg, which is the I've taught it in laws of motion. You have to watch all the videos and the orientation session to know how to approach these lectures, like I've told many times till now. So yeah, I won't be reiterating the concepts. It's going to be a part of your exercise to watch all the lectures. They're indeed going to be helpful. So here type continued, as you can see, there would be another case where, let's say, we have a flask with liquid, then the gravity is going to be acting perpendicular to the surface. So the main takeaway from these two, before I jump into them, is that G effective is always going to be perpendicular to the surface. This is a statement that you have to keep in your mind. And what is G effective? Watch my Newton's laws of motion video, you'll be able to understand what G effective is. In this case, G is equal to G effective. It's obvious because directly it's downward G, and that's it. There is no other factor contributing in it. So let's take case number 2 now. So in case number 2, this flask is being accelerated with an acceleration A towards the right. So if you visualize it, the liquid will now move like this. Like when you accelerate it and pull a flask, like imagine what will happen if you just pull this flask. The liquid will it'll go to that side and it will form something like this. So the statement will still hold true that the G effective will be perpendicular to the surface. So if people were wondering how that happens, then we have to first draw the FBD type of a diagram for this. One would be G acting downwards, and from Newton's law of motion, if you remember pseudo force, we can use the same concept. There would be an opposite acceleration in the free body diagram, and that would give us the resultant G effective, which is at an angle theta with G. So G effective, as you can see, is still perpendicular to the surface, making the statement still hold true. And if you want to know the formula, G effective would be under root G square plus A square, and tan theta would be A by G. It is just from vectors part of the third or the fourth chapter. There's nothing new. You have to just watch those lectures to understand. Now the same case I've taken when it's being accelerated with an A acceleration A, but now what I'm trying to imply is that the line which is parallel to the line over here, as you can see, whenever you take any 2 points on this line, the pressure over there will be the same, which means Pascal's law will still hold true even if accelerated with A, but now the line is kind of parallel to this line. So this is basically the same Pascal's law thing which I mentioned above, but it's for a different type of a setup. That would be type number 3, the problem. Now the next type of problem, this is going to be pretty important. So let's say we have a flask, and then we mark the points A, B, C, and D, and this flask is being accelerated with acceleration A. So when you do that, if you're asked to calculate like any of these terms over here, as you can see, in that case you have to know how to write the equation. So there is a simple trick which I have which I'm going to present it to most of you, which is going to all of you, which is going to be called as from the top. So you have to start from the top with this arrow, like just drop an arrow from the top. It can be from this side or this side. You can do this side as an exercise. So when you start it from the top, you have to first keep in mind that the line will go like this now. Like you chose that side, so the line will now go like this. So you should keep the direction of the arrow in your mind, that the arrow will be like this over here and the arrow will be like this over here. So once you keep the arrow in your mind and the direction, you have to next make sure that you start with PA. At the top it would be PA, right? So we start with PA. Now we add H1 rho G, which means the height over here, this height is H1 and this height over here is H2. I forgot to mention this height is H2, and over here the horizontal length will be L. So you are starting from the top. You will first add PA, and then you will be adding H1 rho G, and then next one, if you see, it's minus rho AL, which means the formula H rho G is still true, but over here H is replaced by L and G is replaced by A, because over here it's horizontal, right? It's A. But the reason why it's negative is because if you remember when I mentioned the FBD that time, A will be like this, but this A is over here when you're pulling it. So that's why it became negative. So same way even the next one will be negative H rho G, but over here it's H2. And if you're wondering why it's negative here, then you should draw the FBD. So G was downwards and the arrow is going upwards. If you remember, the path of the arrow that we chose is something like this. So here the arrow is going upwards, but as you know, G will be downwards. So because it's in the opposite direction, it will be negative. Whereas for this case, it's positive because the arrow is also going downwards and even G is going to act downwards. So that's why it's positive over here. And then again, it will be finally equal to PD. So you're basically making sure that there is conservation happening. I've explained thoroughly and this is going to be helpful. So if you are not able to understand, you can join the Telegram group and ask me the question. It's there in the description. Because this revision series, I'm not like explaining a lot, but you can still join Telegram and ask me for the questions. Next case, as you can see over here, there will be a cylinder, and over here a part of the cylinder, this much, is submerged in a liquid, and the area of surface area over here would be A, as you can see it's shaded, but over here height H1 is going to be the height of the container submerged in water. Listen to me carefully. And height H is going to be the area which is not, no, the height which is not submerged in water. So if this is the case, V1 by V, which means volume of the submerged part by volume which is not submerged, listen carefully, it's the volume of that's not submerged, not the whole volume, is equal to height H1, which is height of the submerged container, by H, which is going to be the part height of the container which is not submerged, is equal to rho of the solid by rho of the liquid, which means density of the solid by density of the liquid. So it's like inverse proportionality. You have to just keep this in your mind too. I'll be just highlighting it. Next one would be the next type of problem, which would be, as you can see, it's more than a type of problem. You can see this as a concept. So when a body, as you can see, is like submerged in water, there would be mg acting downwards, we all know. But now in liquid there would be another force called buoyancy force. It's denoted by u, as you can see, because it's upthrust. You can even call it upthrust force. So that upthrust is equal to Fb, which is F buoyancy force, is equal to V rho g. So the formula is going to be V rho g, as you can see, V rho g. But one thing that you have to know, or in fact I must say it's a very important thing that you have to know, is that rho over here is going to be rho of the liquid, and volume is going to be mass by rho of solid. So if you're wondering why this is so important, we have next concept called as apparent weight, which is going to be mg minus apparent weight is going to be mg minus Fb, and Fb, as you can see over here, is V rho g. So that's what I've written over here. And over here, as you can see, you can replace this V with this formula, and you'll be able to get mg minus m times m divided by rho of the solid into rho of the liquid g. And reading is another formula that you have to know, and I've already mentioned in Newton's laws of motion that reading is going to be something divided by g, and over here that something is going to be apparent weight. So this entire term divided by g is going to be the reading. When you put the measure this on a weighing scale underwater, this is going to be its reading. So I hope apparent weight concept is clear. You have to know how to calculate apparent weight and what the terms mean. Next one will be Archimedes principle. It's pretty popular, like you've been learning it since maybe 9th or 8th. So this container, as you can see, this flask has a solid which has density rho s, and this is liquid which has density rho l. So when you place this solid, some of the liquid will, let's say, overflow. Like you can imagine yourself putting a mug on top of, let's say, a bucket which is full of water. So that time there will be some liquid which will be pouring. So that weight of the water displaced, right, which means weight of the water we just spilled, is equal to upthrust, which is going to be u from this concept, which is again going to be equal to loss of weight of the body, which means apparent weight is always going to be less than the actual weight, which we all know, which means when you place a body underwater, its new weight is called as apparent weight, by the way. If you're wondering what apparent weight is the new weight of the body after being submerged in water. It's always lesser than the actual weight. So if you're wondering where is the weight loss is over here, as you can see from this formula you'll be able to get to know. And other observation is that if the body will sink if the density of solid is greater than liquid, there will be complete submerge of the body. If this is the case, as you can see, I think I'll be just highlighting this, sinks, it will submerge if it's like this. There will be partial submerge which will happen if this is the case. So yeah, you can just keep that in your mind. It might come as an MCQ and you shouldn't get confused. So next one would be type of flow. There is going to be streamlined flow and turbulent flow. Streamlined flow is when velocity is same throughout the flow, and turbulent is going to be when velocity is different throughout the flow. Like if you take any point in the flow, the velocity will be different. Next one would be definition of ideal fluid. Ideal fluid should have a constant density, it should be non-viscous, and it should be having a streamlined flow, and it should not have rotation. So the reason why this is so important is because the upcoming loss over here and the theorem is going to be only for ideal fluids, and you have to know what ideal fluid is. So next one will be equation of continuity. As you can see, there are going to be few theorems and equations and laws from now. So equation of continuity is like, let's say there's a pipe, and the area of cross section over here is A1 and over here is A2, and the velocity of the fluid inside this, the ideal fluid is there, right? The ideal fluid which is inside this pipe, the velocity which goes through A1, and if V2 is the velocity which is of the same fluid when it goes out of A2, in that case A1 V1 is equal to A2 V2, which means if A1 is small, then V1 should be big, and that means this is the relation that you have to infer from it, and I've just mentioned it over there in bracket. Next one will be Bernoulli's theorem. So this is going to be conservation of energy, based on conservation of energy. So as you can see, this is the setup. The terms whichever I mentioned till now will remain the same. Only new terms will be H1, which is going to be height of this part from the floor, H2 height of this part from the floor, P1 which is going to be pressure at this point, P2 pressure at this point, A1 area of cross section over here, and A2 area of cross section over here. V1 V2 will be the same. In this case, P1 plus H1 rho g plus half rho V1 square. So this is similar to kinetic energy, half mv square, but over here m is replaced by density, and that is going to be equal to P2, which is this point's pressure, plus H2 rho g, which means this height rho, plus half rho V2 square. So it's basically like this parts these three is equal to this parts these three. So that's what it is, and usually as you can see, P1 and P2 will be equal to atmospheric pressure itself, so these terms might get cancelled. It depends on what's there in the question. So that would be Bernoulli's theorem for you. Next one would be Torcelli's law, and in this case there will be a flask, and as you can see, if there is a hole over here, then the liquid will be pouring out like this, and R over here would be the range of this pouring out part, which means range, like if you remember in projectile motion we had range, right? It's like that itself, but it's this much. So in this case, if this is going to be height of the entire container and height h from the top of the surface till the hole, in that case V2 is going to be the velocity out of this part. I have not mentioned it here, so I'm going to mention it now. I'll be writing it here. So V2 is going to be over here, the velocity over here, and V1 is going to okay, there is no V1 in this formula, so I won't be mentioning it, but V1 is going to be velocity that this is going to be coming down with. So yeah, as you can see, I've written V2 is equal to 2gh, capital H. Note that it's capital H, it's not going to be it's capital H, it's not going to be small h. So that is V2 formula, and R formula, range formula, is going to be 2 times small h, like 2 times under root small h, capital H minus h. And R is going to be maximum. If they ask you when is range going to be maximum, range is going to be maximum if small h is equal to capital H by 2. So that is Torcelli's law. Next one would be Venturimeter or Venturimeter. I'm not sure how to pronounce it. I think it's Venturimeter. So please do I'm sorry for the mispronunciation. I'm not sure. So this is how the diagram is going to look like. You can look at it in NCERT for a better understanding, because there's another way to draw this same setup. So this is going to be h. You have to know what h is. It's going to be the height difference between the liquid over here and the liquid over here. So that is going to be small h, and in that case this is going to be the formula. You have to know what A1 A2 is. It's there in the diagram, so I won't be like specifying it further. It's there in the diagram also. So yeah, that would be V1. And next one would be viscosity. That would be the next concept. So viscosity, as you can see over here, there will be a liquid over here, the force will be more, and over here it will be less, which means it will start to reduce as you go down. And viscosity FV over here is going to be denoted by minus eta A dV by dy, and you have to know what these terms are. It's important. dV by dy is going to be velocity gradient, and eta over here is going to be coefficient of viscosity. So next one would be Stokes law, and in this case there will be a ball which will be going with velocity v, and it has a radius r in a liquid. In this case, you have to know that one FBD, if you draw its FBD, this is obvious, mg will be acting downwards, but there will be another viscous force which will be acting opposite to it, which is given by this formula. As you can see, I have written the formula. It is 6 eta pi rv. So that's the formula. It's important. I'm highlighting it. And after a point, it will get this constant velocity called as terminal velocity. And as you can see in the graph, it will be constant, which means if you extrapolate it, the velocity that you get over here would be terminal velocity vt. So this velocity over here, as you can see, is going to be given by this formula. So this formula is going to be 2 by 9 g r square delta rho divided by eta, where delta rho is equal to density of solid minus density of liquid, and this is going to be an obvious concept. If vt is equal to constant, a is going to be 0. So next one would be surface tension. As you can see, there are a lot of topics here, more than the chapter size. It's the number of concepts. We have finally come to surface tension, which means we are about to finish the chapter. So surface tension, the definition is given by S is equal to F by L, which means force upon length, and we can rewrite it as F is equal to SL also. It would come in handy in a couple of problems. You can solve past papers and stuff. I've mentioned in my orientation session on what to do once you watch my lectures on, and then you'll be able to get a better idea. So next one will be surface energy. So formula is going to be this, because I've written it in another fashion over there, but this is going to be the formula, and A is surface area, keep it in your mind. So in this case, E is equal to, which means E is going to be surface energy, by the way. Surface energy is equal to S into A. So over here A is surface area, and this is the main formula. So here I've basically given analogy for two types, which is going to be drop and bubble. So drop means it's going to be a water droplet, and bubble, it's obvious that it's going to be a bubble. So in this case, for the drop, the surface energy will be equal to 4 pi r square times surface tension, and it's obvious because the formula is S into A, where A is surface area, and surface area of this circle would be 4 pi r square, where r is the radius. However, for bubble, you have to use the same formula E1. As you can see, this is E1, but you have to multiply it with 2, and this will be used throughout. You're just multiplying it with 2 for bubble, because bubble will be having two surface, like there will be two layers actually. So next one would be excess pressure. This is excess pressure. I'm mentioning it now. It's not given over here, but delta P means excess pressure. So excess pressure, which is denoted by delta P over here, delta P1 is equal to 2 S by R, where S is surface tension, and delta P2, which is going to be just like how I mentioned, it's going to be excess pressure for the bubble, which is 2 times excess pressure of the drop. So as you can see, the same logic is held true. You have to just multiply with 2. Next one will be work done to blow from R1 to R2, which means, let's say the initial radius was R1, and you blow it using some kind of a contraption, and you blow it to a bigger size of radius R2. In this case, if they ask you what is work done, then if you remember from work power energy, work is equal to work is equal to change in U. It depends. This negative depends on the scenario. So using the same concept, we'll be using the same formula here. But one more thing that you have to know here is there would be R2 square minus R1 square. Instead of just R square, you have to use this concept. So this is WD1, which means work done in case of drop. And obviously work done in case of bubble will just be twice the work done in case of a drop. The analogy still holds true. 2 times in just bubble case. So next one would be angle of contact. Next concept, that is. So angle of contact is like, let's say we have taken this scenario, like you can see the drawing over here, but we have just zoomed in on one side of it. We have just zoomed in this much. So if this is the wall of the capillary, and then this is the liquid, then to find the angle of contact, you have to basically draw an arrow like this, as you can see downwards, and you have to draw a dotted line. I think I'll remove the annotation, you'll be able to understand. So you have to draw it like this, and then you have to draw a dotted line, and this angle, as you can see, this theta angle is going to be angle of contact, and over here it's less than 90. In this case, it's less than 90, and over here, what is A greater than C? It means this is observed when adhesive force is greater than cohesive force. Now the same thing, in sometimes what happens is, we'll be able to see it like this. As you can see over here, I've taken this scenario over here, bottom capillary rise. So in that case also, for finding out the angle of contact, you have to just draw a line like this, and then you have to draw the dotted lines like this, and this would be angle of contact, just like how I mentioned all this time. This would be angle of contact, and over here theta is going to be greater than 90 degree. And when does this happen? This happens when adhesive force is less than cohesive force. So you have to keep that in your mind. The last concept, which is going to be capillary rise, you have to just note down what h is. Over here, h is going to be the height difference over here, h. And in this case, h is going to be the height difference over here. As you can see, it's very small, but this is going to be the height, h. This small distance, h. It might not be clear, but yeah, this is going to be h over here. So over here, this is going to be h. In this case, h is going to be equal to 2 times s cos theta. Over here, theta is angle of contact. I think I haven't written, so I'll just mention it. Angle of contact. This theta is angle of contact divided by g rho r. And what is r over here? R is going to be radius of the capillary tube. I'll just mention it over here. So yeah, that would be h. And with this, we have completed the chapter. It took me a lot of time to compile the entire chapter, as you can see. So please do like, subscribe, and also share it with your friends. It really would help the entire community as a whole. And yeah, I think you have to proceed with the other chapters. So work hard, and I'll see you.